Hi, my name is Ian. I'm a member of the Teen Advisory Board with the Howard County Library System, and today we'll be going over L'Hopital's rule. Alright, so before we begin, let's just first do a quick review with a basic limit problem. Evaluate the limit as x approaches 2 of x cubed plus x minus 6 over x cubed minus 4. Simple enough, all we really do right here is we substitute 2 in for x and we solve. So 2 cubed plus 2 minus 6 over 2 cubed minus 4 is our new equation. And then we solve it, and then we get 8 plus 2 minus 6, which is 4 in the numerator, and 8 minus 4 in the denominator, so 4. So our final answer would be 1 for this problem. Simple enough, it's just substituting in our values. Moving on, we're going to look at the first case of L'Hopital's rule. And in do so, let's just first look at an example. Evaluate the limit as x approaches 2 of x squared plus x minus 6 over x squared minus 4. Let's just look at it separated from the numerator and the denominator. Let's look at it separately. But what we're going to do is apply what we did in the first problem to what we're going to do here. So the limit as x approaches 2 of x squared plus x minus 6 equals 2 squared plus 2 minus 6, which gives us 0. That's our numerator. And limit as x approaches 2 of x squared minus 4, so the denominator, equals 2 squared minus 4, which gives us 0. So I hope you realize that this is becoming a problem because we have a 0 in the numerator and denominator. And obviously we cannot divide anything by 0 because the answer would be undefined. There wouldn't be a 1. And we also have a 0 in the numerator as well. So this is actually considered an indeterminate form. And this is one of the indeterminate forms used in L'Hopital's rule. So the first case of L'Hopital's rule states that if the limit as x approaches a of f of x over g of x equals 0 over 0, then the limit as x approaches a of f prime of x over g prime of x equals the limit as x approaches a of the original problem. So what this really means is if our original problem, if we took the limit of the original problem and it gave us an indeterminate form like 0 over 0, then we take the derivative of that problem in order to evaluate the original function. So keeping that in mind, let's take a look at this problem. So what we're going to do is obviously we have an indeterminate form right here. So we're going to take the derivative of that right now. So by L'Hopital's rule, we have the limit as x approaches 2 of, well, let's just take the numerator first, of x squared plus x minus 6. Take the derivative of that, so you get 2x plus 1. And then you evaluate it as we did before, and then we would get 5. And if we repeat that process with the denominator, we get limit as x approaches 2 of the derivative of x squared minus 4. So that will give us 2x. So 2 times 2 equals 4. So as you can see, our new fraction is 5 over 4. Because we took the derivative, we went from 0 over 0 to 5 over 4. And this is actually a real answer. So our final solution would be limit as x approaches 2 of our original equation, so x squared plus x minus 6 over x squared minus 4 equals the new one that we have right here. So the limit as x approaches 2 of 2x plus 1, so the derivative, and over 2x, so the derivative of the denominator as well. And then that left us with 5 over 4, a real answer. And that is going to be our final answer as well. All right, so notice how this was actually in line with the rule, L'Hopital's rule. So we found the derivative of the original function, and it gave us the answer to the original problem. So moving on to case number 2, which is very similar to case 1, we're going to look at a new problem, which is evaluate the limit as x approaches infinity of x squared over e to the x. So similar process, let's just start by substituting in infinity to the original equation. So limit as x approaches infinity of x squared. So we evaluate that, so you get the infinity squared, which just becomes infinity. You take the limit as x approaches infinity of the denominator, which is e to the x, and you would get e to the infinity, which is also infinity. So our new fraction looks like this. Notice how this infinity over infinity looks very similar to our first case, which is just 0 over 0. Again, this is also another indeterminate form that L'Hopital uses. So in this case, it states that if the limit as x approaches a of f of x over g of x equals infinity over infinity, then the limit as x approaches a of f prime over g prime equals the limit as x approaches a of the original function. So once again, it's the same idea that you take the derivative of the original function in order to find the answer. You're evaluating at the rate of change. You're evaluating the rate of change of the function rather than just looking at the values. So the same steps still apply. So let's just once again take the derivative of both the numerator and the denominator. So therefore, by L'Hopital's rule, we have the limit as x approaches infinity of the derivative of the numerator, which is x squared. Derivative of that is 2x. All right. So then we evaluate again. So 2 times infinity, which is just infinity. All right. And then we take the denominator again. So limit as x approaches infinity. The derivative of e to the x is still e to the x. And if we evaluate that again, we would still end up with infinity. So what's interesting here is we took the derivative of the original function, but we still ended up with the same indeterminate form. And so what do you do about it? This leads us to a very important concept in L'Hopital's rule, which is if taking the derivative of the original expression still yields an indeterminate form, then L'Hopital's rule can be repeated until the limit yields a real answer. So if taking the derivative the first time didn't work, you can continue taking the derivative over and over again until the limit yields an actual answer other than an indeterminate form. So if we were to apply that into our original problem, let's take the second derivative. So we would get limit as x approaches infinity. And instead of taking the derivative of this first numerator right here, we're going to take the derivative of this of 2x. And that will leave us with 2. And we'll repeat that with the denominator. The limit as x approaches infinity of e to the x, again, is just e to the x. And if we evaluate it, limit as x approaches infinity of 2 equals 2. And limit as x approaches infinity of e to the x is just e to the infinity, which is infinity. So now we have 2 over infinity. Notice how this is no longer in indeterminate form. And this can actually give us a real answer. Because if you think about it, 2 is a very small number, and infinity is a really, 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 really large number that cannot be quantified. And so this is dividing these two will be like dividing 1 by 1 trillion. The answer will give you a very, very, very small decimal, and that decimal in this case of 2 divided by 2 divided by infinity would be so small that it's negligible, and we can consider it 0. So 2 divided by infinity would be 0. So now. To summarize what we did in this problem, we'll look at the fact that the limit as x approaches infinity of the original problem, so x squared over e to the x, we took the derivative of that, which is limit as x approaches infinity of 2x over e to the x, so again, d over dx, and we saw that it gave us an indeterminate form. So we continued the process, so this became limit as x approaches infinity of 2 over e to the x. And this gave us something other than an indeterminate form. And from there, we were able to evaluate. And we now have 0 as our final answer. And that is the process. To continue taking the derivative until we reach a real answer. All right. So to review, if we combine the two cases of L'Hopital's rule, we get that if the limit of as x approaches a of f of x over g of x equals 0 over 0 or infinity over infinity, then the limit as x approaches a of the derivative of f of x and the derivative of g of x equals the limit as x approaches a of the original function. And that is all there is to it. Taking the derivative of the original function in order to evaluate it. And we only mentioned 2 indeterminate forms in this video, but there are 5 other ones that require manipulation in order for L'Hopital's rule to be applied. And they're all listed below as these 5. But that is a topic for another time. This is where we end today. I hope you found this video useful, and thank you for watching.